Hello everyone, we are a research team from National Chiao Tung University, Taiwan. Today we're going to introduce our work, Single Image Reflection Removal with Edge Guidance, Reflection Classifier, and Recurrent Decomposition. Reflection removal aims to remove undesired reflection from an image captured through a glass, where the reflection-contaminated image I is often modeled as a linear combination of the transmission layer T and the reflection layer R. However, this is extremely challenging since single image reflection removal is an ill-posed problem. There apparently exist infinite ways of decomposing I into T and R if I is provided without additional constraints or priors. Therefore, we propose to use several carefully designed objectives and guidance in our work for alleviating the difficulty of this ill-posed problem from different perspectives. We introduce a deep convolution network with three auxiliary extensions: edge guidance, reflection classifier, and recurrent decomposition. We adopt a state-of-the-art network of reflection removal as the basis for building up our proposed model. Our base model is composed of three cascaded subnetworks, where the first subnetwork takes a reflection-contaminated image I to predict the preliminary transmission. The second subnetwork then estimates the reflection layer based on the input of I and the preliminary transmission. Eventually, the third subnetwork takes I and the predicted reflection layer to output the final estimation of transmission layer. The first of our proposed auxiliary extensions is to have the edge guidance. We are motivated by the observation that gradients of transmission and reflection layers usually exhibit different distributions, where the reflection layer often tends to be more blurry and unclear. Hence, we employ an edge estimator to predict the gradient of the transmission layer from the input image I, and then we use the predicted edge as additional information for guiding our base model. Our second extension, reflection classifier, provides more constraints and objectives to further improve the model learning. The basic intuition behind the design of our reflection classifier is that, as I is an image contaminated by the reflection R, there should exist some structures or local patterns in I that are similar to the ones shown in R. By contrast, the transmission layer T and reflection layer R are typically distinct from each other, so there should be no repeated patterns shared across T and R. Therefore, we can train the reflection classifier based on the positive pairs composed of I and R, as well as the negative ones composed of T and R. We can then use the reflection classifier to distinguish whether our estimated transmission layer still contains reflection. The last extension is recurrent decomposition. The sequential decomposition of our three subnetworks can actually be extended by adding more cascaded subnetworks. However, this leads to more expenses in computation and memory usage. Thus, instead of increasing the number of subnetworks with their weights non-shared, we propose to reuse the second and the third subnetworks again. By using the mechanism of our recurrent decomposition, we can improve the efficacy of our decomposition network to achieve better reflection removal without requiring extra memory to handle the additional subnetworks. Now, we integrate the base model with all three extensions into our full model. First, we use the edge extractor to predict the edge of the transmission layer and exploit it as an additional input for the base model. Second, we use the novel reflection classifier to score the estimated transmission layer obtained during the procedure of decomposition and derive an objective based on the score to improve the model learning. Last, we extend the base model to have the recurrent decomposition by using subnetworks to achieve better results for reflection removal. Here are some results of our method. Since our method considers both the edge information and the remaining reflection in estimation, it can handle the reflection well while retaining clear structure. Moreover, by using the recurrent decomposition, the efficacy of our model is boosted with those information twice, thus leading to results with better preserved details and correct color. Please visit our session to know more details and have discussion with us. Many thanks for your attention.